Oh, hi guys. So I imagine you printed the pages off for today, and as they were coming out of your printer, you were probably looking at them thinking, what the heck is this? This looks unlike anything we've ever done in this class. Let me assure you that circuits look scary on the page, but it's the easiest stuff that we're going to do. You're not even going to need a calculator today. You're going to be able to do everything just in your head. Let's go through some notes. I know you started this stuff in grade 9, and actually you did this in grade 9. You did this work in grade 9. It just wasn't called, you probably didn't see this title, Kirchhoff or Kirchhoff, however you say it. I think it's Kirchhoff. You didn't see that as a title. You just learned some laws for circuits and there was no name. So chances are you actually did this before. Over here on the side is a reminder of some of the symbols that are involved when you're drawing circuits. We are not using all those symbols. You actually had to learn them in grade 9, I think. We are not using those symbols whatsoever. There's a couple important ones. You need to know a battery. You need to know connecting wires, which is obviously just a line. And you need to know resistors and lamps. And really they're kind of the same thing. They're both loads, items that could be drawn in a circuit. So like I drew two diagrams here just to show you that that's all we're using. Remember from grade 9 you learned two types of circuits, series and parallel. In a series circuit, all of the loads, and in grade 9 they're most often drawn as lamps, all of the loads are along the same wire in a row in a series. There's only one path going around that circuit. In a parallel circuit, there are several different paths that electricity can take. And the benefit to having several different paths is if one of these paths gets wrecked, you still have other paths that electricity will still follow. So in a lot of devices, you want things to be wired in parallel because if something happens to one part of the circuit, you don't want the whole circuit to die. The best example, you can write it down off to the side if you want, is a car. Try to imagine all the electrical components in your car, and let's say that the one that I X'd out right there is one of your headlights. And these are your dashboard lights and the radio. You're driving down the road, a rock flies up and smashes one of your headlights. Well, if that happened, you don't want the entire electrical system of the car to be dead. Just imagine if you're driving down the road and suddenly, instantly, your dashboard lights go out, your radio dies, and you have no electrical power. In a series circuit, if one of these components got knocked out, the entire circuit would be dead. There would be no other way for electricity to flow around the rest of the circuit because there's only one path. But this is cheaper and obviously requires less material. So you often get, like for example, Christmas lights are often wired in series, whereas if one of your lights burns out, the entire strand is dead. And you got to try and figure out which of the 50 lights on the strand was the one strand that burnt out. Anyway, what is today's work about? These Kirchhoff laws. I cut and pasted them here in these gray boxes. And let me tell you something. When you try and read a formula description for Kirchhoff's laws for what happens to current in a series circuit and what happens to voltage in a series circuit, you are not going to remember these. I don't care how many times you stare at them. You're not going to remember what this formula looks like or what that formula looks like. And your grade 9 teacher probably made you somehow try and remember these little formulas. I am telling you right now, you will drive yourself nuts if you try and remember what's in these gray boxes. You need to just understand what the heck happens. What is current? What is voltage? If you understand what it is, you do not need these shaded in boxes and you do not need to remember them. Let me try and explain it slowly, and you can make rough notes if you want. I don't know how you want to do this. Think about what current is. Current is the flow of electricity leaving this battery. So, and ignore these little dots that are drawn all over the place here. They're just drawing dots on here to indicate that there was a closed switch here and that these dots are like the start and the end of the lamp. Ignore the dots. The dots mean nothing. They shouldn't even be on there. Imagine an electron, and I'm going to draw it as a dot. That's why I don't want to confuse you with these other ones. Imagine an electron leaving the battery and traveling through the circuit. That's what current is the flow of electrons. That electron has only one way to go. It's going to pass through the very first load, in this case a lamp, and it's going to pass through it and go to the next one. So just think about that. This electron has nowhere else to go. The current of this electron, whatever this current is, I'll label it as an I. When it passes through the first load, the current of that load is going to be exactly the same as the current that left the battery. Think of it as water in a garden hose. All the water that leaves the battery is going to flow through this load and continue on and flow through the next one and continue on and flow through the next one. That's why this formula is that the currents are all equal. It's very easy to understand if you think about it like that, and don't try and memorize it, and don't look at these shaded in boxes. Just think, a series circuit, current is like water flowing through the circuit. It's got nowhere to split up, nowhere else to go, so it's just going to be the same through the whole thing. If you use that exact same idea and think about current in a parallel circuit, and don't even look at this. I have nothing to cover it up with, my calculator. Don't even look at that. Just think about it. If current leaves the battery and starts to flow through this circuit, think of it as water in a garden hose. As soon as it hits this junction, it's got 3 different ways that it can go. And it can't skip one of those ways. It's water, it's current. It's going to divide up and it's going to go every way possible. But yeah, it's going to split, and it's going to split evenly among these 3 loads. Not necessarily splitting evenly, but right now at this grade level, it's going to split evenly. So you are going to get current in this load, I'll call it current 1. You're going to get current in this load, current 2, and you're going to get current in this load, current 3. But it's going to split up. And if you added up all of those currents, you would get the original current again when it flows back to the battery. So there's the idea. In a parallel circuit, you have to add them up. The current will split. It won't be the same as it was in the battery. It'll split up into different little subcurrents, and you need to add all those up to know how much current you had in the beginning. And that's exactly what they're trying to show here, that the current in a parallel circuit will be the addition of all the little currents that you find across the parallel. Easy? It should be easy to think about it like that. Current is the easy one to understand. Voltage is going to be a little bit trickier, but I'm going to try and explain it. Okay, but current is the easiest thing to understand, so always start with current, because you can think of current as water. On the next page, I left some space for some rough notes. I was going to try and scribble on there, but let's write on here instead. Let's try to understand what voltage is. When an electron leaves the battery, I want you to think about this. The electrons are carrying energy. So when the electron passes through the battery, it collects energy at the battery. I'm going to draw that as like a circle around it. Just think about it like that. There's the electron traveling away from the battery, and it is carrying energy. That energy needs to be dumped off at the load, or the loads if there are more than one, and all of that energy has to be dumped off before that electron goes back to the battery. It can't go back to the battery having any voltage whatsoever. It has to lose all of it, and it's got to deliver it. It's got to drop it off, and it can't drop off 0. There has to be an amount of energy delivered to each one of these loads. So think about this. If you are an electron carrying a package of energy, and you need to deliver some to each one of these loads, you're going to deliver a little bit to the first one, a little bit to the second one, a little bit to the third, and then you'll have 0. And you're going to go back to the battery. Well, that means that you have to, if you wanted to know how much voltage you had in the beginning, you would have to add these up. If you dropped off a little bit here, and a little bit there, and finally a little bit here, the only way you would know how much you had in the beginning was add them all up. That's exactly what, going back to the first page, is shown right here. That the voltage in a series circuit is the addition of the individual voltages that you find in the loads. But you're not going to remember that if you look at it in a shaded box. You're not going to remember why. You're not going to remember whether you add them up or whether they're the same. You got to think sensibly like this. Think about what voltage is. It's energy, and it gets delivered. It gets dropped off. You have to drop off some to every load in the circuit and go back with 0. So what would happen in a parallel circuit if you use that exact same idea? Every electron leaving the battery, and I'll draw a dot for an electron again, not to be confused with the dots on this line. Each electron has a package of energy that it has picked up at the battery. Okay? Each one. And when they hit this point right here, there are 3 different ways to go. Current splits up, but each individual electron can't split up. Each electron has to turn to the left or to the right or go straight ahead. And after each one of them is going to pass through one of these loads, and then here they're all going to come back together again and continue on. Well, remember what I said. They have to drop off energy, and they can't go back to the battery with any of it left. So each one of the electrons that goes 3 different directions here is going to encounter one and only one load and then go back to the battery. So the one that turns to the left is going to go through here, drop off all its energy, and back to the battery it goes. The one that goes through the middle will drop off all of its energy and back to the battery it goes. The one that goes to the right will drop off all its energy and back to the battery it goes. They lose all their energy when they pass through that one component. So the rule in written print, unfortunately, the rule for a parallel circuit is voltage in parallel, they are all the same. They're the same because the same amount gets dumped off to the first one as would be to the second one to the third one, because all the energy from the battery gets dumped off. What does this mean? Because I'm sure right now you're just totally confused. You hear me talking, you're looking at your page, you might have hit pause a few times, wrote some things down, but it's still meaningless in your head. And that's what you're going to find with simple circuit electricity work. You can't do it theoretically. You just have to do it. You just have to practice it and see how easy it is. So go back to this sheet. I put some numbers here. Just to let's finish these diagrams with these numbers. If you had a battery with 6 amps of electricity flowing out of it, and each one of those electrons is carrying 120 volts, the 6 amps of current will all flow through this component. So this will also be 6 amps because it's all going to go through there. The second component, all of it's going to flow through. That'll be 6 amps as well. The third component, all of it will flow through. That'll be 6 amps as well. Just like the law states, in a series circuit, current is the same throughout the entire circuit. Voltage, there's 120 volts. You would have to have some other numbers on this diagram. They wouldn't be able to leave it completely blank. But let's say that they told you that the voltage here was 20 and that the voltage here was 30. And they wanted you to solve for the voltage here. Well, the idea is, in a series circuit, little bits of voltage have to be dumped off at each one of the components, but you got to go back to the battery with nothing left. So if 20 got dropped off here and 30 got dropped off here, and it was a 120 volt circuit, this would have to be 70, because then it would all get dumped off. 20, 30, 20 and 30 is 50, 70 is 120, and you're back to 0 when you hit the battery again. In the parallel circuit, let's try the same idea. Voltage is 120. You leave the battery carrying 120 volts of electricity. No matter which way you go here, you're going to dump it all off and go back to the battery. So this voltage would be 120. This one would be 120. This one would be 120. The current, 6 amps, when it hits this junction, it's going to split. And right now at this grade level, we'll just say that it splits evenly. Some of the current goes left, some goes right, some goes forward. So each one of these would be 2 amps. add them all up, and you get the original current again going back to the battery, 6 amps. I'm sighing because I know how confusing this is, especially when you're trying to learn it remotely like this. But what needs to happen is you need to do some simple examples so that you can see that you get it. Here's what a typical question looked like last year on the exam and on tests. You would get a circuit. It would be either series or parallel, or sometimes a mix of the two. But right now, in this example, there's a series circuit, and there's a chart with some information given for different things in the circuit, and then the rest of the chart is blank. And the question was always the same, just fill in the chart. My suggestion when you get questions like this is take whatever's in the chart and transfer the information into the diagram. It's a lot easier if you can see it in the place where it's supposed to be in the diagram. So what I would do is say this. It says that lamp 1 has a current of 3 amps. So I would write that right here. Here's lamp 1. Current equals 3 amps. The voltage of the battery is 120 V. I would write that right on the diagram. Battery voltage 120 V. And then instead of looking at the chart and trying to figure out which space is going to have which value in it, ignore the chart. Just look at the diagram and say, okay, I want to fill in a V and an I for every place on this diagram. VI, 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 VI. Every single one of these components is going to have a voltage and a current, including the battery. And just follow your rules and ask yourself, what are they going to be? In this case, the current is 3 amps, and it's a series circuit. That means that every single one of the electrons that flow through this lamp already flowed through lamp 2, already flowed through lamp 3, unless it was the other direction, and they're all going to go back through the battery. There is no other way to go. The current in this circuit is the current in this circuit. They're all going to be 3. You could go back to your formulas and try to look at the shaded boxes for the formulas to understand that, but my suggestion is don't. The voltage, 120 volts leaves the battery, and it's got to be dumped off bit by bit by bit across this circuit. And you can't go back to the battery with any voltage left over. Now I'm going to tell you, in this circuit, it would split up evenly just because the currents are all even. So if you had 120 volts and you had to deliver some to each one of these components and the same amount to each component and go back with 0, then the only sensible answer is that it would be 40 volts, 40 volts, and 40 volts, because that would equal 120. So the current does not split, the voltage does. And then you could fill in your chart. Each one of these would be 3 amps, 3 amps, 3 amps, and the voltage would split up. 40 volts, 40 volts, 40 volts. Okay, I want you to try one on your own, right here. Actually, this is a series circuit again. So hold that thought. Try this one on your own. Yeah, try this one on your own. See if you can fill in each one of these missing spaces using the same theory. Okay? You don't have to show any calculations. That's what's nice about this. You can just understand and write down the numbers based on the numbers that you already have. So think about it, and we're going to take this one up. Don't be concerned that the diagram has these little lightning bolts for resistors instead of lamps. They're still loads. They still do exactly the same thing. Energy still gets dropped off, etc. See if you can fill in this. Top of the next page is a parallel circuit. So without me even doing it as an example, see if you can fill in this circuit, given the information that's provided on the page. Actually, I would prefer if you do this one right now. So again, take the information that you have in the chart, You can leave it in the chart if you want, but it's a little bit better if you transfer it and actually see it. So what I would do is I would say, okay, so the voltage of lamp 2, that's here, is 70. The voltage of lamp 3 is 70. And you're being asked to fill in voltage for lamp 1 and the voltage back at the battery. The most common mistake here is to say that this voltage has to be 70 because the other ones are 70. That's actually right. That's not the mistake. The mistake is adding all three of these up and saying back at the battery that the voltage therefore must be 70 plus 70 plus 70. 210 volts. That's the most common mistake. That's not the case. Every single electron that hits this junction is going to dump all of its energy off at whatever resistor it flows through, and they're all going to go back to the battery with nothing, where they're going to pick up a reload of voltage and head back again. So the voltage is not 210. You don't add them all up. It's 70. The battery's 70 and it provides 70. That's the only hint I'm going to give you. Now finish off the rest of the chart. Do the current. And then finally, for those of you that have done this before, you're probably going to find this really easy. For those of you that haven't, you're not even going to know whether you're doing this right. Try a question which is a mixed circuit. Here's a question that would have been a series circuit, but stuck in the middle of this branch on the series circuit is a parallel part. So normally it would have been in series, but you've got this to deal with. What the heck happens? I'm telling you right now, you will not be able to stare at formulas on a formula sheet and figure out those answers. You have to be able to think sensibly. Try this one. You don't have to do any further reading. You don't have to do any further examples. You just need to understand what happens to current and what happens to voltage. So take these numbers that are in the chart at the bottom, write them in the diagram in the places that are indicated by the titles in the chart, and see if you can look at the diagram and come up with some ideas as to what happens to the current in the rest of the diagram and what happens to the voltage in the rest, and see if you can fill in these missing 5 spaces in the chart. We're going to take all of this up. Don't worry if you get any of this wrong. And I'm not just going to take this up by posting answers, because posting written answers isn't going to do any good. So the actual take-up for this work is probably going to be a video take-up that I'm going to want you to watch, because that's the only way that you'll really understand it. But try this work today. It's going to take you 10 minutes. You do not need a calculator. Well, I mean, there's some minor subtraction that you may have to do. Maybe you will need a calculator. But what I mean is you're not going to use any formulas. You don't have to rearrange anything. You don't have to substitute values into anything. It's just going to be a matter of figuring out these spaces. So try it on your own, and we'll take it up, and we'll see if you get it. This last question I wrote down, use your intuition. Okay, so it's, use your intuition. It's not a question where you need examples. Just think sensibly. They're like little puzzles. Okay, that's all for today. I'm going to leave you with those 3 questions. Take them up, get your answers, write your answers in the chart, and let's see if you make any mistakes.